Take it over.
So in this second part, I'm going to be focusing on econometrics in auctions in particular. It was that branch of the figure where you had continuous actions, but now this table we will impose more structure that we're in an auction. So I'm going to be focusing primarily in identification and estimation in first price auctions, and then I'll briefly talk about other works that go beyond the first price auction setting. So first price auctions are important. For instance, many of the procurement auctions are first price auctions. And so that's examples where these things have been applied in empirical papers. What is the goal? We have deployed a sealed bid first price auction where people submit a bid, the highest bidder wins, and they pay their bid for the item. We'll assume that bidders' values for the item are drawn from some distribution F, that's common. And what we observe is the submitted bids for the auction. And we have multiple such samples of different auctions that happened and the bid vectors that were submitted. And we're going to assume that the bids that people submit come from a symmetric Bayes Nash equilibrium. Then the identification question is, if we observe the bid distribution of that symmetric Bayes Nash equilibrium, let's call that G. So this is the distribution of bids under a symmetric Bayes Nash equilibrium. Can we reverse engineer and calculate F, the distribution of values? So let's first try to argue that yes, you can do it. You can reverse engineer, and there's a one-to-one mapping between F and G. And if I give you G, you can tell me what F is. And that will also give us an approach for estimation if we have samples from the distribution and don't know exactly the whole distribution. So at the symmetric equilibrium, we can write the following equation. If a player imagines that he is some other value, Z, and submits based on the equilibrium strategy of that other value, Z, so submits a bid of S of Z, then whenever they win, they're going to pay S of Z. Their value is V, so this is their utility whenever they win. And their probability of winning is the probability that all other players have a type that's smaller than Z. Because it's a monotone symmetric equilibrium, if they have a type smaller than Z, they will be bidding also lower than Z, and so I'm going to be winning. Now, if this S is an equilibrium, it must be that when I'm maximizing this quantity over here, the value that I'm going to be getting for Z is my value, V. Right? So I'm going to be behaving as if I am my value when I'm maximizing my utility.
So I'm confused. Is this S of V equal to Syrgkanis? I'm confused. So
no, this is your maximizing over types that you could be pretending to be.
oh, it's good.
So these are the first order condition in the case that Z equals V, that it is our request.
Exactly. So let's write now the first order condition of this objective and evaluate it at the optimum, which is V. Right? So we take the derivative of this. This is going to be what we get out. We evaluate it at V. It has to be equal to 0. And then you can solve for V. And you're going to get that V is, you can write V as a function of the equilibrium bid, the derivative of the equilibrium bid, and the distribution of player values, and also the density of the player of that distribution. Now you can also do a change of variables. Say B, which is my B, is S of V.
Sorry, you assume, sorry, I'm sorry.
Huh?
You assume a monotone
Monotone,
equilibrium.
symmetric equilibrium, yes.
Okay, sorry.
The distribution of bits, let's write down the density, is the probability that a random draw from that S of V, where V is drawn from F, is smaller than B. So it's the probability that some random draw V from F is smaller than the inverse of B. So the density, the CDF of the distribution of bits, you can write it as a function of the CDF of the distribution of values and the equilibrium and the inverse of the equilibrium strategy. And similarly, the density of the distribution of bits, you can take the derivative of this equation here, and you can write it as a function of the density of the distribution of values and some property and the equilibrium strategy. Now, if you go up to this equation over here and make the change of variables, we're going to write V be the inverse of some bit B, and S of V is equal to B. And then the nice thing here is that the S prime divided by F is going to be equal to the density of the distribution of bits. And in the numerator, you're going to have the CDF of the distribution of bits. So you have this sort of nice cancellation due to this formula. So what does this say? It says that my value, the hidden value, which is the inverse of the equilibrium strategy for the bit that I observed, can be written in a unique manner as a function of the bid and the observed distributions. So these are the distributions that someone gives me. These are distributions of bids. And now, given those distributions of bids, if you give me a bid of a player, I can give you what their value was. Right? That's what this says. It says that if you give me what bid you submitted, and you also gave me what is the equilibrium CDF and PDF, I can then reverse engineer and tell you what that hidden value is, V, if that symmetric monotone equilibrium assumption was satisfied. Okay. So because you can do that, then you can essentially estimate the CDF and the PDF of the distribution of values. Because for every bit that you observe in the sample, you can reverse engineer what their value was. Okay? If someone gave you the equilibrium CDF and PDF. And so now you essentially have, if in the population limit, you essentially have samples from values. And then it's a matter of saying, okay, I give you samples from values, you can find what the CDF is and the PDF is. You can also write it down formally based on these mappings, but that's the idea. Right? So that means that the distribution of values is point identified if someone gives you access to the distribution of bids.
Are you going to discuss rates? Or
briefly, yeah. So then this gives also rise to a reasonable estimation strategy. If given that you told me that if I give you this the CDF and the PDF of the distribution of bids, then I can roughly get approximate samples of the values of players. What I can do to estimate, I can estimate the empirical CDF given an empirical distribution of bids. I can estimate an empirical PDF using some standard kernel-based estimators. So this basically sort of counts in some, like stylistically, this just counts, splits the space into bins and counts how many things are in bins, but it does it in a smooth manner. Okay? That's a kernel density estimator. And so these will be consistent at some rates. And then I can,
Out of curiosity, does it matter the kernel what it would be?
So as long as it satisfies some derivative conditions, it achieves the optimal non-parametric rates for estimating a PDF. But yeah,
is something that typically people are using.
The kernel density estimator, yes. Then you have also you need to tune like the bandwidth and things like that. There are auto tuning procedures. It's like this is more standard. Like
which kernel are you using typically?
Oh, people are using, I don't know, they call this a Panetsnikov kernel. There's like different types of kernels. Even if you just use like a standard like plotting package out there, like in Python or R, it will have some kernel density estimator in the backend with some optimized bandwidth to give you a nice density function.
So just to be sure, instead of doing a histogram and finding the portion bins, you're trying to find something that will interpolate also.
Yeah, you're trying to find a smooth G function, right? You're not gonna do a step function. Okay.
So if I understand correctly, S was not known, right? In the
S was not?
Did you end up learning S as well in the previous setup?
No.
So you were not told what the equilibrium is, right? You just observed the distribution.
Yeah, but exactly. I was only told, I only observed the distribution. So S1 is from here.
I think the question would be, as the question it is, you feel that for different bids, you learn the inverse of the strategy. So you can.
I mean, you could, you do get this, so you could try to invert it, true. But yes. So yes. I mean, you don't use it. You don't argue about like estimation rates for this per se, but you're saying how accurate is the value that I got from that inversion, and especially when I plug it into the second stage where I calculate the CDFs and PDF. But yes, this also gives you this. You can empirically estimate this. You can empirically estimate that gives you the inverse of that, and so. But it has to be that the assumption is that it is a symmetric and monotone equilibrium for all of these calculations to be correct. So then given these estimates, capital G hat and small g hat, I can do a plug-in, plug them into that formula and get an approximate estimate of the value of a player, which is going to be approximate because this is not really the correct distribution of bids at equilibrium. It's only an empirical analog of them. And so for every sample of bids in my data, I'm going to get a sample from the values. And then I can define similarly empirical analogs of the CDF of the values by looking at how many values fall below every V, and also do like a kernel-based estimator of the density. So that's the approach proposed in this paper, the GPV paper. This is heavily cited.
It's like a function to be invertible, requires the G function to be regular, or like satisfy some condition. So
it has to be like like strictly monotone equilibrium. Otherwise, even the first formula where I said that being below it wouldn't hold. But
so
yes.
that makes me wonder that if you go with a kernel approach to estimate G, you may not end up like satisfying that assumption. Would that be okay? If you estimate the G using the Kernel method, you may end up having a distribution that does not necessarily satisfy the monotone has already done.
I don't think I
Are you
ever.
gonna break down everything, or are you gonna like?
I never did the self-consistency. Are you saying the self-consistency? Like after you estimate distribution of values, you can then compose it with S and see if you get back G. Yes, you never go back and do that. You just you something you do in one part. You never say okay, now I have a distribution of values. I also have an approximate estimate of my S. Let me compose them and see if I get G back.
Because I think that the whole formula that you came up with is based on this monotonicity of S function.
Yes.
To make it invertible.
Yes.
But then if you end up like estimating G, distribution G, and then that does not, for example, satisfy monotone has already or like some similar condition. So the whole then your S's may not be invertible. And I'm just wondering if that's okay with the whole with the theoretical result as well as its performance.
Could it be that this thing is not monotone? Yeah.
I think for like like for Myerson, like then I use like data on like using kernel method to estimate distribution of the beats, and then that ended up like being having like a weird shape.
Let me take this offline because maybe that if you do the calculations here, you might always be getting monotone, but like let me take it offline. I'm not sure that it will be a problem if you take the derivative of this, what you end up with, and it might be some benign assumption on the estimates that will give you monotonicity. Yeah. Yeah. Anyway, so maybe by taking the derivatives of this with respect to B, you'll see what you need from the estimate to be monotone. But I mean, the G's are gonna cancel out. I don't know. Yeah, it's like not to yeah. To do online.
Some fail assumption, I think.
Mm.
Kind of like an example of second derivative. Right? But the second derivative capital G will appear.
Yeah, I guess it would be fun if you get like a normal mapping at bits map, yeah, lower bits map to higher values. How do we count it? And then there's also the question about rates you get, and the paper provides some non-parametric rates subject to regularity conditions. If the density of the values are uniformly bounded continuous derivatives, then you can get rates for the density of the distribution of bids that scale slightly worse than the rates that you would get if you were actually observing samples from the values directly. So you, instead of getting n to the minus r over 2r plus 1, which is what you would get for density estimation, non-parametric density estimation, in 1D you get like a slightly worse exponent in the rate. So and that's because to estimate the density of f, we need that depends on the derivative of the estimate of the density of G, and this extra derivative that you're taking is what leads to the worse rates.
This is in what norm are you?
I believe it's in the sup norm
Of the cumulative?
of the PDF.
The PDF. So point, it's not like a. What's it?
Yeah.
It's norm of the.
So this is not total variation distance?
No, that's uniform. Yeah, that's why I think you also have the log in the denominator.
It's not a.
It's like you just the worst case difference of the PDF over the domain. Typically, there should be some 0-1 domain or bound.
Like typically for kernel methods, even the constant depends on the actual distribution. So it's like the rates that you get depend on the object. Yes, it's not like it's more of a. It's not like the computer science approach, which is like some absolute constant that does not depend on the instance. But it's more like yeah, the order depends on the distribution you're trying to estimate, correct? This is what happens with kernel methods typically.
The concept. Yeah. I mean,
I mean, unless you know a lot about the derivatives of it, like.
you'll get some bounds on those derivatives, but yeah. If you assume some further bounds on those, you could have a worst case over a class. Okay. I'm gonna. There's also been work if only the winning bid is observed, but I'm gonna skip that and get to the next. To get to the next section. So another notable literature is going beyond the independent private value that I mentioned. So there's this seminal work of Arthur and Hale that looks at affiliated private values, but for second price and ascending auctions, where the winning price and the bidder is observed. But primarily it only asks about the identification question and not the estimation question. So just tells you when is the distribution of values point identified if I give you the distribution of bids.
Even if it's symmetric. I mean, because like even in the IPP setting for asymmetric distributions, there's not much work as far as
no, that is more work than there is an estimation. I think the a subset of the authors of GPP have looked at some asymmetric, but again,
So okay, so your comment here is even for symmetric, there's only identification.
For current for common value or affiliated private value, there's mostly identification. In this paper, and estimation strategies, yeah, need to look further because there will be some more recent papers. Another paper looks at what happens if I give you, say, if I look at ascending auctions, but bids are observed only in increments, which is typical in ascending auctions. So the price goes up by some minimum increment of say $5 or whatever. And so then you don't really observe, you don't have like a continuous strategy space. Even if my optimal bid is 5.5, I only need to bid either 5 or 10. And that leads to problems where because of that discontinuity of the bid space, you get partial identification of the private value. You can only infer a set and of CDFs where your true CDF should lie in, so you don't get point identification. If you want like a more complete treatment of structure of the current state of structural estimation in auctions, there is this book by Pars and Hong that goes over all of these different streams.
What's the IPP?
Independent private values. So some main takeaways from that literature is that closed form solutions of equilibrium bid functions in auctions allows for non-parametric identification of the unobserved value distribution. So in you can non-parametrically, as opposed to the types of estimation strategies we had in the previous part, where we made some parametric assumptions on the private SOCs. Here you can non-parametrically identify the private value distribution. And there's this sort of like easy two-stage estimation strategies where you estimate observed bid distributions and then plug them into sort of like an analog of the best response equation and get back the distribution of values.
Do we ever really expect independent private values to hold? Like options or keyword options or even as
yeah, you can imagine, yeah, fully independent, maybe not, but maybe if many of the things in abstraction, you could have like observed characteristics of the object, and then some things are known and they all shifted, and then the private SOCs to those values are independent. So you would have common shifters that are known, maybe even to the auctioneer, of the quality of the object, and then the other SOCs are independent. Like my cost of production, if I'm in a procurement auction, could just be independent for different firms. Yeah.
Typically used as a model of my understanding is for non-durable goods. good. It's not an oil field, but like I want to go to the movies, so I'm going to go to the movies, and that's over. And tomorrow I'm going to go again. So I cannot be say. I mean, okay. If there's resale value of my ticket to the movie theater, it's a different story.
But I guess one way of thinking about this is that if I observe the valuation of my rival, is that going to tell something about how much I should value? For instance, in advertising options, the idea is that if I acquire a pair of eyeballs, is how much I value those eyeballs is going to depend on how much my rival values those eyeballs. And I think typically the answer is no, right? Unless my rival knows about how much this guy is going to spend on my item, which is right. So it's not completely, I think, makes sense.
Yeah.
Right?
So for this, so sponsored search and stuff is a good example of non-durable goods. I get the eyeballs and I get some value out of it. But like, for example, bidding on an oil field, if I know that you have a good signal for the oil field, then that informs my the use of that.
And the point is not symmetric.
Where?
Like in these results, like the one we saw was symmetric. But they can do without.
I think there's also papers on symmetric, but yeah. And then the rates for estimating density of the value distribution are typically quite slow. So that's the drawback of these approaches. But look at the uniform convergence rate of the density. So in the remainder, I'll go into two papers from the computer science literature that try to tackle some of the drawbacks of the literature so far. The first one is trying to address the issue of these slow rates and say if we really care about optimizing over a space of mechanisms with respect to revenue, we don't really need to estimate those value distributions and their CDFs and their PDFs at these slow rates. We can get root and rates for estimating the revenue of any counterfactual auction in that class, and so we can optimize at faster rates. And the second one was a paper we did with Eva and Dennis, where we were trying to relax the equilibrium assumption and see what we can say when you do value inference in online ad auctions, subject to the assumption that players use a no-regret learning algorithm, connecting it to the topics that were discussed so far in the tutorials. So the first paper aimed to identify a class of auctions such that by observing bits from the equilibrium of one auction, you can infer the equilibrium revenue of any other auction in the class in a fast, the fast estimation rate. And such that the class of auctions that we consider contains auctions with high revenue always for any distribution of values compared to the optimal auction that we could have run even outside of the class. So the class of auctions that were analyzed were the ones called rank-based auctions. So these are position auctions where every position has a weight in a decreasing weight, and bidders are allocated to positions based on their relative rank of their bid. So the kth highest bidder gets allocation xk, and pays xk times bk. The feasibility constraint is that because the amount of sort of allocation I assign to the top tau bidders should not be more than the allocation that's there in the top tau slots. So this is the class of auctions. And it is known that for regular distributions, the best such rank-based auction is two approximation to the optimal auction. So it achieves at least half of the revenue of the optimal auction for the given distribution of values.
Just to be sure, the best rank is with the meaning is a specific auction model, or with the meaning that if we get the, what does it mean, the best rank?
Well, if I can choose the W's.
Oh, that means, okay.
Sorry. If I can, sorry, if I am constrained to have this visibility. No, if I can choose, yeah, okay.
The optimal W's in the auction, that is the meaning of the best rank based auction.
No, I think it's.
Can you explain the auction?
Yes. So I have this this slots W1 to WN with these weights, okay, and bidder submits. I can
What do the weight capture?
the weight capture say, you know, the first slot has a probability of click of 0.9. The second slot has a probability of click of 0.8. Bidders arrive and I submit bids, and in some sense the auction does not look at the actual value of those bids, just looks at the rank. Okay, so the top bidder.
This is a pay-per-click.
Yeah, I mean, yes. You should think if you want a story, yes, but like it's just a class of auctions. Yeah. So the top bidder is going to be allocated to these bids based on some. It's going to be randomly allocated on those slots with some distribution. The second highest bidder is going to be allocated to the slots with some other distribution, and so on and so forth. Overall, they're going to get some allocation from these assignments, and that allocation is going to be xk, which is sort of like the total allocation that they get from each of those randomly assigned slots, and
Xk is a vector.
no, xk is the sort of like the sum of those allocation probabilities.
Oh,
So you can think of the this is the sort of like the mechanics of the auction, but you can also think of them equivalently as each bidder getting some total allocation xk, and paying first price. So xk is sort of my total allocation times bk, but because these xk come from randomly assigning bidders to these slots, those allocations have to satisfy these sort of like prefix constraints that I cannot allocate to the top tau bidders more than what is there in the top tau slots. Okay. Yeah, maybe there's a motonistic of it. Okay. But yeah. This is maybe the most the confusing statement. Maybe this is the class of auctions. You just need to look at the these last three bullets. But this is sort of like how you implement it. And I think the optimality is not what I said before. It's sort of like among all auctions with such feasibility constraints, what is what optimal revenue could you have achieved?
Okay.
And the constraints here is that, you know, like you only look at the round of the bids, and you're also allowed to, you're charging first price. And yeah.
Just to be sure, the allocations are a continuous number between 0 and 1, or 0 and WI. So that means that it's dividable, the item that I am. Okay.
And you can think of it as mechanistically as probability. So.
Okay.
So what is strange about the feasibility constraint is it's on the ranks. It's not on the. So I here represents the rank.
Yeah.
You have feasibility constraints on, you know, not your typical feasibility constraint, which is on the what's the overall allocation across all bidders? Like why? So the feasibility is. So like if I look at the bottom 3 bullets there, it's hard. I mean, at the bottom, I don't know. Like I guess a first price auction and like the last 2 bullets. So first price auction. It's not that my typical feasibility constraint. Because it uses ranks for feasibility constraint, right?
So I think like in a ranking option or position option, there's not taking care about the permutation. But then these XIs or XK does not provide the double permutation. It gives us that this probability. Think like this this bidder in the composition. It is probably this bidder in the second position. So now the question is that if I give you those probabilities, can you come up with consistent permutation? For those probabilities. So this feasibility constraint ensures that for those probabilities there exists like ranking and some probability over permutation.
So maybe the constraint is just I can choose any way to assign those slots to bidders, and this is just what comes out of, and the constraint is that these are the feasibility constraints. Like I choose an assignment, and the space of allocations that come out have to satisfy these. If all I'm doing is ranking people based on their bids. So every rank-based auction can be viewed as a new position auction with a different set of weights that satisfy these prefix feasibility constraints. Like you can view every such rank-based auction as a new position auction where these are the weights of the position auction, and I'm assigning people to positions, and they get W1 bar or W2 bar based on the position that they are allocated to, so there's no randomization. And so the auctioneer's optimizations over such modifications to the setting. And such position auctions is also equivalent to running a mixture over k unit auctions, where the probability of running the kth unit auction is the difference between this WK bar and WK plus 1 bar. So you can show, after all these manipulations, that all of these rank-based auctions that we talked in the previous slide are equivalent to choosing a mixture over k unit auctions, PK. And so where I run the kth unit auction with some probability PK, and these PKs are things that I can optimize over, right? Subject to the constraints that are coming from the original feasibility constraints. So optimizing over rank-based auctions is equivalent to optimizing over the space of randomizations over k unit auctions, whereby k unit auction, I mean I have k equally valued units, each has an allocation of 1. And if you get one of those units, you get an allocation of 1. If you don't, you get an allocation of 0. And you pay your bid if you are allocated a unit. Right? So this is the simple k unit auction. And so then the question is to calculate the revenue of any rank-based auction. It's equivalent to calculating the revenue of any such k unit auction for the distribution of values of the player in the setting. So we decompose the revenue of any rank-based auction into mixtures over revenues of rank-based of k unit auctions, and so it suffices to calculate the expected revenue RK of each of those k unit auctions. So the main question that was asked in that paper is that if I give you one rank-based auction, and I give you bids from the equilibrium of that rank-based auction, can you calculate the revenue of any other such k unit auction, which would then allow you to calculate the counterfactual revenue of any other auction in the class?
so I'm confused. What is this? Are the people symmetric?
Yes.
This setting?
Yes.
So they're the way, I mean, so it's a first price auction, right? So you're not using the truthfulness at all here in the statement you're making.
Yeah.
But you're using someone of the least good ability.
In what?
I don't know, I mean,
I'm
so
not
like the bidders bid before, so you announce it, like, when you say distribution over unit auctions, you mean I have a set of allocation rules and price rules,
yes.
and I put a distribution over those. I announce a distribution, and then people have to bid, right? So my question is, how do they bid when facing distribution over?
Yes, and we're going to assume a model equilibrium.
Okay.
Symmetric model equilibrium again. But the point is to get rid of the slow end to the 1/4, but sorry, the slow rate that we were getting for the PDF for this quantity over here, which was RK. So if we don't care about getting the PDF of the values in this model of equilibrium, but we just care about estimating RK, which is the revenue we would have gotten for that for whatever distribution of values, if we were to run a K-unit auction, then we can optimize over that space of auctions. So the approach that was used is again trying to write the best response conditions, but now does a transformation of variables, and instead of talking about values, we're going to be talking about quantiles of values. So instead of talking about the actual absolute value of a player, we're going to be talking about its quantile, which is equivalent to the rank of a player if I were to order sort of like the percentile of a player, right? In the top 10 percentile, the top 15 percentile, and so on and so forth. And the reason why this is useful is also because first there's like a one-to-one mapping, and also because the auction only uses ranks, and the equilibrium is symmetric. This is really only what matters, what percentile of the distribution you are. So you can write a similar formula that you don't want to deviate to any other bid, and you can write after first order conditions as a similar first order condition, a similar inversion equation as the one that we arrived in when analyzing the GPV paper, where the value of the player is their bid at equilibrium, and here the derivative of the bid is roughly connected to the density in the CDF. Now the nice thing is that this quantity over here, which is the allocation probability as a function of your quantile, and the derivative of the allocation probability as a function of your quantile, are known from the rules of the auction. Because the auction only uses ranks and the equilibrium is monotone. These are sort of like quantities that the auctioneer that we know just from the rules of the auction. What is your probability of allocation if you're in the top 10 percentile, which will also mean that you're in the top 10 percentile of the bid distribution, and that is just the rules of the auction. So this we don't need to estimate; we can just plug in. And the only thing that remains to estimate from the observed data are B and B prime, and which is sort of like the B of Q. You can think of it as the inverse of the CDF of the distribution of bids. And B prime is the derivative of that inverse, which will contain both CDFs and densities. So B prime is really the problematic part because it contains a density of the observed distribution of bids. If we want to get rid of the slow rates, in some sense, we need to get rid of that derivative, which will be estimable only at slower rates. So you can see also these mappings here. B of Q is really the inverse of the CDF. B prime is 1 over the density. And so this is sort of like an equivalent formulation as the GPV. So the main message of that paper is that the quantity RK depends only on B of Q and not on B prime of Q, and this will lead to fast rates. And the reason that you can do that is because the revenue is really an expectation over quantiles of quantities that that contain the estimated value that we recover. So even though for recovering the actual value of a player, you crucially depend on B prime, when you calculate the expected revenue in another option, even though V of Q enters there, the recovered V, it only enters into an expectation, and that expectation will smoothen out the objective. And by doing some integration by parts, you can get rid of the derivative in that quantity. And so it's this smoothening that comes out of the fact that we're looking at an expected revenue quantity and not at the actual recovering the actual value of a particular player that that gives you the smoothening. And this just does this doing integration by parts from the lecture. And with this, you can get one over root n rates for that revenue RK, since B of Q is essentially the same as estimating a CDF, the CDF of the distribution of bits, and inverted. Of course, you need to, for the inversion to not mess things up, you need some assumptions about the probability of allocation of your mechanism. And the first paper required that the mechanism had a strictly monotone allocation, but that was dropped later on using other tricks in subsequent papers. So that's the main idea, because many times we might care about quantities that are sort of like expected values of hard to estimate quantities. We can get rid of the slower rates and get faster rates.
Out of curiosity, was a mathematical trick or a game theoretic change to avoid the strict positiveness of the?
More just more like a mathematical statistics.
Okay. Just because it seems interesting how you make it happen that it is always well defined.
So so the main message of that paper is by isolating the mechanism designed to rank-based options, we can achieve constant approximation to the optimal revenue, even if we could run any other option, and estimation rates of revenue of each of these options in the class at root n rates. So and so this allows, if you are building a system that optimizes over these options, you can do it with fewer samples. You can do A/B testing between options with and succeed with fewer samples. So in the last part, I'm going to be briefly also connecting to the previous tutorials and talking about what if we drop the equilibrium assumption and assume that players play according to some learning algorithm. Can we still do some form of econometrics and reverse engineer the private values? So in this paper, we analyzed repeated strategic interactions like in an ad auction setting, where for a finite time horizon, players are learning over time. We're not going to be looking at this dynamic Markov perfect equilibrium that I mentioned in the previous session, but we're going to be looking at no regret learning behavior. So we're going to be assuming that the actions of the players that we observe satisfy the no regret property. And by now, I guess we've seen what no regret means in many tutorials, so I'm going to be going fast. So given that this is the only thing that we assume about the observed data, can we reverse engineer and learn the values of the players? And basically, the approach is that these sets of inequalities are going to give you again a partial identification of the parameters of the underlying parameters, primarily because you also have this wiggle room epsilon here, which you don't know exactly what it is, so you don't know exactly what how the level of regret of players have, and so the no regret assumption is basically going to give you a set of inequalities that your true parameter needs to satisfy, and there might be multiple values theta that satisfy these slack best response constraints.
So just a clarifying question about the setting. Is this a repeated interaction with the same set of players?
Yes, yeah. So assume like a sponsor search auction where we bid on that same keyword all the time.
So you're learning simultaneously on both strategy and values.
Yes, okay, we can assume like that there's a private value that you know, that you, at least the advertiser, knows the private value, but you don't really need to, for a no-regret algorithm to work, you don't really need to know the value, you just need to get like banded feedback every day to respond, like, and then you can use a banded learning algorithm.
The value stays the same.
Yes, the value stays the same in this one, yes. That is maybe the most restrictive part of this.
With the meaning that I want to buy something today, if I don't have it today, maybe it's more important for me tomorrow.
No, this is more like, like that the value for a click of an advertiser remains the same for, say, a period of a week that we can analyze, which is the value of someone visiting, an average user visiting the web page and buying something.
So the assumption is that rivals are playing equilibrium conditional on their value, or that rivals are playing whatever.
Rivals could be playing anything as long as I am satisfying the no-regret condition. I'm going to infer your private value. So for different values of epsilon, these constraints are going to be giving us different sets of parameters that are rationalizable. And then you can, basically what these constraints are going to be giving us a set that is the identified set. And then from samples, you can try to estimate that identified set. When we are looking at particularly auction settings and say sponsor search auction settings, where players have some value per click and the utilities have this quasi-linear form, where this is your value for a click, this is your allocation probability, and this is your payment. Then these identified sets are also going to be taking some nicer forms because you have this, you're trying to identify the rationalizable set for this value vi, and you have this quasi-linear particular utility. So back then we analyzed 9 frequent bid changing advertiser. Each advertiser has bids on many keywords and studied the data for a period of a week. These were the types of data that we were looking at, and we were getting sort of rationalizable sets, which for the particular type of utility you can show they're going to be these convex sets. And the question is, okay, if you want to predict the value for a player, what do you do? Like, what is the level of regret that is reasonable? And what point prediction could you use to say perform a prediction in the future? Back then we proposed that one uses the lowest value of regret. Subsequent work of Noti and Nissan proposed a quantal regret solution to this problem, where they chose some distribution over points in that lower end of the curve. Some evidence that this could be a reasonable solution concept. We were observing that the regret over time was dropping from one week to the next for the recovered value that we observed. And if you're sort of saying, okay, so is this a reasonable assumption that people learn based on these no regret rules over time? It's hard to do that just by doing the empirical strategy of identifying of recovering the private values. One thing that you could try to do is not only recover private values, but also try to predict future bids from past behavior based on such structural assumptions that people are playing based on a no regret rule. And so in a more recent work, what we did was to simultaneously try to infer both the update rule that they were using in this no regret framework and also the private parameters in their utility. And particularly, we looked at one of the most widely used sort of like online learning algorithms, so online gradient descent and its generalizations of follow the regularized leaders that many people talked about in the previous tutorials. This is going to be a no regret algorithm if the utilities were continuous and concave, which, because of the randomness of the auction, many times they tend to satisfy these properties, at least for a large region of the bids. And so this gives you some formulas of how the bids should be looking between two periods of a player, and then using the data you can infer the parameters of those update rules, which is sort of like the step size and the private value, and use those parameters to extrapolate in the future and predict bids.
What is this thing about random step size?
One way to view like fitting a model that fits this data is to say that eta is what is the interpretation of the error if you run this regression. You can view it as some sort of like random step size, or you can also view it as the value changing over time. This is the source.
Noisy.
Yeah, no, this is like if you're trying to fit the data to this, it won't fit you perfectly, right? So when you run the regression, it's going to be an error. What would that error be coming from? So that's that. And that's what we did. We tried to see how well it predicts. The key place to look at where is it? Is this one over here, where the most important thing is how does it predict when the test distribution is different from the training distribution, which is the more important part. Where, as I was saying, these structural methods could be more relevant when you're trying to predict out of sample. So here we try to say, let's look at the two periods of 2 days where, like 2 periods of during the day where the distributions of bids are very different. So day and night were very different. So let's train models on the solely on the day data and predict the bids of players on the night data. And over here, we were observing that, for instance, in the series prediction, where you try to predict the whole series of bids of the player in the next few days, this is the best you could do with machine learning time series approaches, and in particular this Prophet algorithm from Facebook. And you see that OGD-based methods perform even better than some state-of-the-art time series prediction methods from machine learning. So even though OGD is a very simple parametric model, it was performing better than these more complicated, fancy machine learning approaches when there was a covariate shift. And when there wasn't, it was comparable.
So by series prediction, you mean several steps in the future?
Yeah. And step ahead is I see your last bid, I predict your next period bid. So let me conclude. What I think are some potential points of interaction between the TCS community and the structural econometric theory literature is things that have already been done so far are in terms of objectives like Wolfram revenue and combined with approximation bounds. So these are some papers that already been there. So instead of looking at recovering distributions of values, we can just look directly at whatever you're trying to maximize. The other thing is computational complexity of proposed econometric methods. Many of the methods that I mentioned, especially in the dynamic game setting, were very inefficient when you're trying to implement it. Many of them use some grid search methods where you just search over a grid of parameters in a d-dimensional space. So finding more computationally efficient alternative estimation procedures. Many of the econometric methods are not applied to game structures that we have studied exhaustively in the algorithmic game theory community, such as routing games or simple auctions, and maybe we can look at different classes of games that we have studied from econometric perspective, especially when the game models have a combinatorial flavor, like combinatorial auctions. The econometric theory in auctions for combinatorial auctions is a pretty open area. And then we can look at computational learning theory techniques and online learning theory techniques applied to econometrics, like recovering distributions with more benign distribution distances and with better finite sample errors, and more generally looking more at finite sample properties of our estimators, which is more what we try to do, maybe in the computational learning theory community, but maybe in more stylized settings than the ones that have been analyzed in econometric theory papers. That's it. Thank you very much.
We went a bit over time, but let's take questions that you may have. Yeah.
Yeah. So I was thinking about conceptually, the last exercise, one way of executing it could have been thinking about the Bayesian updating, right, as learning. So think about agents repeatedly interacting and doing Bayesian updating based on the observed beats. So you're doing something else, right? So what's the right way of thinking about these? One possibility could be, I'm thinking about a market in which these learning algorithms are deployed instead of, say, Bayesian rationalizers that I want to predict. Is that?
Yeah, that's because most of these automated bidding tools are doing some form of online learning algorithms, especially because in these markets the mechanism is very opaque and the feedback is very opaque. It's not that I really know all of the mechanics of the mechanism or how I'm allocated here, how I'm allocated there. Many times the feedback is in the form of you got this many clicks and you have to pay this much. So it looks more like I submit a bid, I get some utility feedback. And this looks more like an online learning setting where I submit bids and I get back from this black box what utility I derived, and that's exactly where these algorithms were designed for. And so it might be hard to form beliefs about exactly what's going on in the bid matching algorithm in the auction or in the keyword matching and all of these, or like I was matched here, I was not there, and form beliefs about all of these, so that I can basically update given the price I was charged and the number of clicks I got. Yeah.
So one thing that you could do with this exercise, you could sort of test, no? If you have a good fit, that would be sort of evidence that indeed no regret learning is.
Yeah, that's what we tried to do with the bid prediction. That was one place where you could have you're trying to predict, and are you predicting better? Fit is always a bit hard to because you have this partially identified structure, and so you could fit. It's not clear what fit means when you're in this partially identified setting. The other question is what level of regret are you saying is a good fit or not? Because you can also choose what level of regret, and that's why we were showing there were in most players you could rationalize the bids with a small level of regret. So that was a meaning of fit. And in most players, we would see that the smallest level of regret would drop between 2 weeks. So somehow that would be another instance of that the regret is going down. These were the figures that I saw here.
And then one last comment, I promise. So the one natural question could be, what if I know that my rival is using a particular learning paradigm, can I try to exploit it in an adversarial way, like trying to teach him something that could eventually.
But then if you go down that path, you go back to actual equilibria. I mean, in some sense, here you're in the market.
I'm iterating once, right?
Yeah.
If you iterate infinitely often, then you go back.
Yeah.
Thinking about adversarial attacks in this framework, assuming that one bidder is learning.
Maybe disconnected with that. I was thinking, if you know that everyone else is paying FTRL, but you will not play, is there something extremely better that you can play?
These are good questions. I mean, one flavor of such results is Matt has some results of when people play like that, the auctioneer can manipulate and get a lot of revenue. That's one style of results. If the auctioneer knows that they're playing exactly these things, I can push them in the right direction and extract the old welfare as revenue. But here, I guess I'm not saying that people know that the other player is playing a particular type of algorithm. It's like playing any algorithm that could have small regret, which could be anything. So then it's not clear what attack I can do if that's my knowledge set. Maybe if I know exactly, like in the final setup where I was saying the other player is using gradient descent, online gradient descent, maybe I can do an attack. But if all I know is that they're using some no regret, it's not clear what the attack would be.
All right. Let's have it out for the morning session.